Before we jump in, let me make one thing clear. This isn't a story about proving anyone right or wrong. It's about a scientific result that's challenging one of the biggest assumptions in modern chip manufacturing. And if that assumption is changing, the entire conversation changes with it. Intel spent years arguing that sub-Angstrom manufacturing without EUV wasn't simply difficult. The claim was stronger than that. The argument was that physics itself was becoming the barrier. And yet, a Chinese research team recently published results that appear to move directly into territory many people assumed required the most advanced extreme ultraviolet systems on Earth. Those two statements should not comfortably coexist. Because when most people hear sub-Angstrom, they imagine a smaller version of the same race we've been watching for 20 years. Smaller transistors, smaller features, smaller nodes. The familiar story. But the paper published by the Chinese lab points towards something different. Not necessarily a replacement for EUV. Not a magic machine. Something potentially more disruptive. A different route. That distinction matters because the semiconductor industry has spent over a decade organizing itself around a single assumption. The most advanced chips require access to the most advanced lithography systems. Remove the tools, and progress slows. Remove enough tools, and progress stops. Entire export control policies were built on that logic. Billions of dollars were allocated around that logic. Some of the most consequential technology restrictions of the last decade depend on that logic remaining true. If another pathway begins to emerge, even a limited one, the conversation changes. The reason this story caught my attention isn't the headline. It's the reaction. Notice what happened after the publication. Most coverage immediately split into two camps. One side declared it proof that sanctions had failed. The other dismissed it as laboratory theater with no industrial relevance. I'm not convinced either side has earned that confidence. Because history suggests something uncomfortable. Many of the technologies that eventually reshaped industries looked irrelevant when they first appeared in academic journals. Remember that. We'll come back to it. To understand why this publication generated so much discussion, we need to talk about the wall the semiconductor industry has been approaching for years. As transistors shrink, the challenge isn't simply making things smaller. The challenge is controlling matter with absurd precision. A nanometer is already difficult for the human brain to visualize. An angstrom is 1/10 of that. We're talking about dimensions approaching the scale of individual atoms. At that level, engineering starts behaving more like negotiation with nature. Every vibration matters. Every imperfection matters. Every manufacturing variation becomes expensive. This is why EUV became so important. Companies such as ASML spent decades building machines capable of projecting patterns at wavelengths that previous generations simply couldn't achieve. The complexity became legendary. Mirrors polished to astonishing tolerances. Supply chains spanning multiple countries. Components that sounded more like physics experiments than factory equipment. The result was an ecosystem so difficult to reproduce that many analysts considered it effectively protected by time itself. That was the assumption. The Chinese publication raises a question, not an answer, but a question. What if progress at atomic scales doesn't always follow the path industry leaders expect? That's where things become interesting. The paper itself isn't claiming that China has suddenly replaced every EUV machine on the planet. Anyone making that argument is getting ahead of the evidence. Laboratory success and industrial production are very different worlds. The graveyard of technology history is full of brilliant demonstrations that never survived contact with manufacturing reality. But dismissing the result outright creates a different problem. Scientific capability compounds. Researchers publish. Other researchers improve the work. Methods become processes. Processes become prototypes. Then one day, an idea everyone ignored becomes a factory line. My opinion is that the most important part of this announcement isn't the reported result itself, It's the fact that researchers are actively searching for routes around constraints, rather than waiting for constraints to disappear. That's usually how technological surprises begin. The real question is whether this publication represents a dead-end experiment or the first visible step of a longer journey. And the answer may depend less on physics than on something far more difficult: turning a laboratory achievement into repeatable industrial reality. The easiest mistake to make is assuming that semiconductor progress is determined by a single machine. It isn't. A chip only becomes real after hundreds of manufacturing steps succeed in sequence. Lithography is one of the most demanding stages, but it lives inside an ecosystem that includes materials science, metrology, chemical engineering, deposition, etching, packaging, and software capable of measuring defects smaller than a virus. That's why this Chinese publication deserves attention for a reason most headlines skipped. It reflects an increasingly mature research ecosystem, rather than one isolated experiment. Over the past decade, China has dramatically expanded funding through institutions like the National Natural Science Foundation, provincial laboratories, and university industry partnerships. Western analysts often focus on commercial firms such as SMIC or Huawei, but much of the long-term competition begins inside research laboratories years before products reach consumers. That's the part financial markets rarely price correctly. Think back to Japan during the 1970s, or South Korea in the 1990s. Their breakthroughs didn't appear overnight. Papers accumulated, patents accumulated. Graduate researchers became startup founders. Suppliers improved one component at a time until outsiders suddenly declared they had appeared. In reality, everyone simply ignored the construction process. Could the same thing be happening again? Possibly. One underappreciated aspect of semiconductor research is that failure is incredibly productive. A laboratory may spend 3 years pursuing an approach that never reaches commercial production, yet discover measurement techniques, fabrication methods, or simulation tools that become valuable somewhere else. Knowledge rarely dies where it was created. It migrates. That's why judging a publication solely by whether it immediately replaces EUV misses the bigger picture. Imagine climbing a mountain where the obvious trail has been blocked. Most people assume the journey ends there. Engineers usually start looking for another path. Sometimes that alternative route turns out to be longer, sometimes slower. Occasionally it becomes the preferred road because it avoids obstacles no one anticipated. This may be one of those moments, or it may not. I'm deliberately leaving room for uncertainty, because semiconductor history has punished overconfidence from every direction. The American counterargument is straightforward and deserves to be taken seriously. Publishing an impressive laboratory result does not mean high-volume manufacturing is close. Modern chip fabrication requires extraordinary consistency. Producing one successful wafer inside a controlled research environment is fundamentally different from producing tens of thousands every month with commercially acceptable defect rates. That distinction has defeated plenty of ambitious technologies before. Even so, there is another reality that's becoming difficult to ignore. China no longer measures success only by catching today's leaders. Increasingly, researchers are asking whether today's roadmap is the only roadmap available. That's a much more interesting question. It also explains why export controls don't always produce predictable outcomes. Restrictions can delay access to existing technology, while simultaneously increasing incentives to investigate entirely different approaches. History offers more than one example of pressure accelerating innovation instead of preventing it. Not always, not automatically, but often enough that policymakers have learned to respect unintended consequences. Here's my doubt. Are we watching the beginning of a genuine manufacturing alternative? Or are observers projecting industrial significance onto what remains an academic milestone? Right now, I don't think anyone can answer that honestly. What we can say is this: the publication exists, the engineering challenge is real, and multiple research groups around the world will almost certainly examine these findings closely. Because even if only 5% of the reported approach survives industrial scrutiny, that 5% could influence how the next generation of lithography evolves. Sometimes a scientific paper doesn't rewrite an industry. It simply plants the idea that the industry has more than one future. There's another layer to this story that rarely makes headlines because it's less dramatic than sanctions or scientific papers. Manufacturing economics. Even if tomorrow someone proved beyond doubt that a sub-Angstrom process could work without conventional EUV, the next question would be brutally simple. Can anyone afford to build it at scale? That's where engineering stops being a laboratory discipline and becomes an industrial one. A semiconductor company isn't rewarded for producing the world's most elegant prototype. It's rewarded for producing millions of reliable chips at a price customers will actually pay. This is where I think the discussion becomes more nuanced. We've treated EUV as though it's the destination. In reality, it's one solution to an exceptionally difficult manufacturing problem. If another method eventually delivers comparable precision with different trade-offs, perhaps requiring more process steps but cheaper equipment, or sacrificing speed for flexibility, it doesn't have to replace EUV completely to reshape the industry. It only needs to become commercially useful somewhere. Consider what happened with chip packaging. For years, shrinking transistors carried most of the industry's attention. Then companies like AMD demonstrated that advanced chiplet architectures could extract enormous performance gains without relying exclusively on the smallest process nodes. Suddenly, packaging wasn't merely a supporting technology. It became part of the competitive advantage. The lesson wasn't that transistor scaling had become irrelevant. It was that innovation had expanded sideways, instead of moving in only one direction. Lithography could experience something similar. That possibility deserves serious consideration, because semiconductor progress has never followed a perfectly straight line. Every generation eventually encounters diminishing returns, forcing engineers to rethink assumptions they once treated as permanent. Here's the reversal that changed my own perspective. When I first read about this publication, I instinctively framed it as a China versus America story. The more I looked at it, the less convincing that framing became. This is increasingly a story about competing engineering philosophies. One philosophy says the existing roadmap is difficult but proven. Invest enormous capital, improve the current system, and continue refining it. The other asks whether an entirely different pathway might eventually achieve comparable results through different physics, different materials, or different manufacturing sequences. Neither philosophy guarantees success. Both involve enormous risk. One simply carries less uncertainty because industry has already committed hundreds of billions of dollars to it. That commitment matters. Existing fabrication plants, supervisor networks, software ecosystems, and highly specialized workforces are built around today's manufacturing processes. Replacing any portion of that infrastructure isn't like updating a smartphone. It's closer to redesigning an airport while flights continue landing every minute. Which brings us back to the Chinese laboratory. Even if their published work ultimately proves impossible to commercialize, it still performs another function. It expands the range of ideas serious researchers are willing to investigate. Scientific competition often works this way. One paper introduces a concept, another group identifies weaknesses, a third improves the methodology. Years later, the final technology barely resembles the original publication, yet none of it would have existed without that first imperfect attempt. My opinion is that too many observers treat research papers as verdicts instead of opening arguments. They're neither victories nor failures. They're invitations for the global scientific community to test, challenge, reproduce, and refine an idea. My prediction is that we'll see significantly more publications exploring alternatives to traditional lithography over the next 5 years. Not because EUV is disappearing, but because every major semiconductor nation understands the danger of relying on only one technological pathway. And perhaps that's the most important takeaway. The publication itself may or may not reshape semiconductor manufacturing. The willingness to question what the industry once called physically impossible already has. Let's go back to where we started. For years, one of the strongest assumptions in the semiconductor world was that the path toward atomic-scale manufacturing had become extraordinarily narrow. If you wanted to keep shrinking features, the accepted answer was simple. More advanced EUV systems, more expensive fabrication plants, and supply chains that only a handful of countries could support. The Chinese laboratory's publication doesn't automatically invalidate that assumption, but it does force us to ask whether the assumption was ever as absolute as we believed. That's an important distinction. Technology rarely advances because someone proves the experts wrong overnight. More often, it advances because enough researchers keep asking questions that eventually expose a path no one thought was practical. Aviation, batteries, artificial intelligence, even modern semiconductor manufacturing itself followed that pattern. Yesterday's impossibility has a habit of becoming tomorrow's engineering challenge. Of course, caution still matters. Independent verification will determine whether the reported results can be reproduced by laboratories outside China. Then comes an even harder test: converting scientific success into repeatable manufacturing with competitive yields, acceptable costs, and long-term reliability. Those hurdles have defeated many promising ideas before. Anyone claiming this paper has already overturned the global semiconductor industry is moving far faster than the available evidence. At the same time, dismissing it because it originated from a Chinese laboratory would be equally unwise. Science doesn't care about political narratives. A measurement is either reproducible or it isn't. A manufacturing process either scales or it doesn't. Reality eventually settles the argument. That, in my view, is what makes this story larger than one research paper. It's really about how technological leadership evolves. For decades, advanced semiconductor capability was concentrated among a relatively small group of companies and countries. That concentration created remarkable innovation, but it also encouraged the belief that future breakthroughs would emerge from the same familiar institutions. History rarely rewards that kind of certainty. Every generation of technology produces new entrants who begin by solving problems the established leaders considered secondary. Sometimes those newcomers disappear. Sometimes they become the next generation of leaders. The semiconductor industry has reached a point where the next major leap may come from unexpected directions rather than familiar ones. It could emerge from a university laboratory instead of a multinational corporation. It could involve new materials, alternative lithography techniques, advanced packaging, computational manufacturing, or approaches that haven't yet reached public discussion. The field has become too large for any single roadmap to define its future. My opinion is that governments should certainly protect strategically important technologies, but they should also recognize a simple reality. Restricting today's tools does not automatically restrict tomorrow's ideas. Ideas travel differently. They evolve. They combine with other discoveries. Eventually, they surprise everyone. So here's the prediction I'm willing to make. Over the next decade, the semiconductor race will become less about who owns one critical machine and more about who builds the most adaptable innovation ecosystem. Countries capable of combining research universities, manufacturing expertise, private investment, software development, material science, and patient industrial policy will have the greatest advantage. That's a much harder competition to win. It's also much harder to sanction. Whether this particular Chinese publication becomes a historical milestone or a scientific footnote remains uncertain. Time and independent replication will decide that. What already seems clear is that the definition of physically impossible has become a little less permanent than many people assumed. And in semiconductor history, that's often where the next chapter begins. If you enjoyed this analysis, consider subscribing and let me know what technology race you'd like us to examine next. The most interesting stories are usually the ones still being argued about, not the ones everyone already agrees on.